Sets and subsets. A set is a collection of objects. The objects in the set are called elements. Two sets are said to be equal if they contain exactly the same elements. We use capital letters to denote sets. Example: given two sets, A equal to the set containing A, B, and C, and B equal to the set containing B, C, and A. We say that the two sets are equal using the notation A equals B. Collections have no order, so the elements of A and B are exactly the same. We say A is an element of set A using the following highlighted notation. If a set is empty, we can represent that with brackets with nothing between them, or we also use the Greek letter phi to represent the empty set. But notice that phi does not equal the set containing phi, because the set on the left, the phi, is empty, and the set on the right contains one element phi between its set brackets. We write the cardinality of S to denote the number of elements in S, and this is called the cardinality of the set. The symbols look identical to the symbols we use for absolute value of a number. If S equals the set containing M, N, O, and P, then the cardinality of S equals 4. That is because there are 4 elements in the set. The cardinality of phi, the empty set, is 0. The cardinality of the set containing the empty set is 1 because it has one element, the empty set. Well-known sets of numbers have letters that mathematicians use to represent them that you should be familiar with. N is used for the set of natural numbers, and those are the counting numbers, 1, 2, 3, 4, and that goes on infinitely. Z we use to represent the set of integers, the positive and negative whole numbers, which are infinite in both the positive and negative direction. Q represents a set of rational numbers. Rational numbers are those numbers that you can represent as a fraction, A over B, where A and B are elements of the integers, except that B doesn't equal 0. We use capital R for the set of real numbers. We can also use a plus or minus sign to indicate only the positives or the negatives of one of these sets, as in Z plus, the positive integers, is the same set as the natural numbers n. Describing sets. Sometimes we list the elements of a set, such as S equals the set 1, 2, 3, 4, 5, and 6, or S equals the infinite set 1, 2, 3, 4, and continue on in the same manner forever. The ellipsis says go on forever. Other times we describe the elements of a set. For example, B equals the set of n, which are elements of the set of integers where n squared is less than or equal to 9. And if we looked at how else that set could be written, those would be the set of numbers -3, -2, -1, 0, 1, 2, and 3. because all of those integers, n had to be an integer, all of those integers when squared gives you a value that's less than or equal to 9, and no other integer squared is less than or equal to 9. Definition of a subset. A set A is called a subset of a set B, written as you see in the highlighted region, if every element of A belongs to B. For example, if we have a set S, and that set contains the integers 1, 2, 3, 4, 5, 6, and 7, if we look at set A, which contains the integers 1, 3, 5, and 7, we know that A is a subset of S because each and every element of A is in S. 1 is in A, 1 is in S. 3 is in A, 3 is in S. 5 is in A, 5 is in S. 7 is in A, and 7 is in S. Set B is the set containing 2, 4, 6, 8. B is not a subset of S, and you see how that's written in the highlighted area. It's a subset sign with a slash through it. B is not a subset of S because 8 is in B, but 8 is not in S. The null set is a subset of S. In fact, the null set is a subset of every set because everything in the null set or the empty set is nothing, so trivially it is an S. The set S is also a subset of itself because everything in S is also in S. The set of integers Z is a subset of the real numbers because every integer is a real number. Two sets A and B are equal, that is, A equals B, if they have precisely the same elements. Or in other words, using the definition of subsets, two sets are equal if and only if A is a subset of B and B is also a subset of A. Example: let A equal the set containing A, B, C, B equal the set containing A and C, C equal the set containing A, B, and C. We notice that B is a subset of A because A is in B and A is in A. Also, C is in B and C is in A. But the reverse is not true. A is not a subset of B, and that's because A contains B and B is not in B. So A does not equal B. C is a subset of A because every element of C is also in A. A is in A, B is in A, C is in A. And likewise, A is a subset of C because A is in C, B is in C, C is in C. So A equals C. Definition: a set A is a proper subset of set B written, as you see in the highlighted region, if A is a subset of B, but A doesn't equal B. For example, consider the sets A containing 1, 2, 3, and 4, B containing 1 and 2, and C containing 1, 2, 3, and 4. B is a subset of A, and also B is a proper subset of A. C is a subset of A, but C is not a proper subset of A. The difference being is, in the first case, everything in B is also in A, but A has some things B doesn't, so they're not equal. In the second case, C is a subset of A, because everything in C is also in A, but C is not a proper subset of A because C and A contain exactly the same thing, and A does not have any elements that are not in C. Often when there is a discussion concerning sets, the sets involved are all subsets of some specific set, which we call the universal set. John Venn gave us what we call Venn diagrams, which was a convenient way to use a visual representation of sets. For example, here, the universal set U is a set containing the letters A, B, C, D, E, and F. You see 3 Venn diagrams. The outside rectangle of each represents U, the universal set, and you see in each picture all of the lowercase letters A through F are inside the universal set, which is the outside rectangle. The first Venn diagram on the left represents the set A that contains A, B, and E. The middle Venn diagram shows you both set A and set C, and they overlap, and A is in both. And in set A on the right, EB is only in A, and set C on the left, D is in C but not in A, and C and F are in neither set A or set C. In the Venn diagram on the right, we have the same universal set, and we see all the letters A through F inside the universal set. In this case, B is the set containing A and E. A is a set containing not only A and E, but also B. So B is contained entirely within set A, so B is a subset of A. Power sets. Definition. The set of all subsets of a set A is called the power set of A and is denoted by the symbols P of A that you see highlighted. The power set of set A is equal to the set containing the sets B, such that B is a subset of A. Example. Let our set A be the set containing A, B, and C. The power set is the set that contains, well, the empty set, because that's a subset of every set, the singleton set containing A, the singleton set containing B, and the singleton set containing C. The sets of cardinality 2, first the set of A and B, next the set of A and C, next the set of B and C, and then finally A itself, the set containing A, B, and C. If we count those, you will see 1, 2, 3, 4, 5, 6, 7, 8 subsets of the set A, and the set of those subsets is the power set of A. In general, if a set A has cardinality n, in our case, our cardinality of our set A in the example is 3, where n is a non-negative integer, then the cardinality of the power set of A is 2 to the n. And in our case, the cardinality of A was 3, so the cardinality of the power set is known to be 2 to the third, or 8.